Something happened off the Pacific Northwest coast this summer that did not get the attention it deserved. And when you understand what it means in the context of what scientists have been publishing about the Cascadia Subduction Zone in 2026, the picture becomes considerably more serious than the headline number alone suggests. A magnitude 5 earthquake struck off the southern Oregon coast on June 29, 2026, at the southern doorstep of the Cascadia Subduction Zone, the locked megathrust fault system that scientists have been warning about for decades. That earthquake did not arrive in a vacuum. It arrived in the middle of a period when new research has fundamentally revised what seismologists thought they understood about the most dangerous fault in North America. And 3 of those revisions, all published in the first half of 2026, point in the same direction. The risk is larger than the previous models described. Welcome to John's Global Guide. Let's break down exactly what is happening at the northern Cascadia boundary, what the new science says, and why this matters for every person living in the Pacific Northwest right now. Let's start with the fault itself, because to understand why any earthquake in this zone deserves careful attention, you need to understand what the Cascadia Subduction Zone actually is and what it is capable of. The Cascadia Subduction Zone is a roughly north-south oriented megathrust earthquake fault that exists offshore from Cape Mendocino, California, to Vancouver Island, British Columbia, and is roughly 700 miles long. It is capable of generating a great earthquake of magnitude 9.0, which is comparable to some of the most powerful and violent earthquakes observed anywhere on Earth. Examples of what that kind of rupture looks like in practice are not theoretical. The 2011 Tohoku earthquake in Japan was a magnitude 9. 0, the northern Sumatra earthquake of 2004, was a magnitude 9. 1. Both generated devastating tsunamis that killed hundreds of thousands of people combined. The Cascadia Subduction Zone has not produced an earthquake since 1700 and is building up pressure where the Juan de Fuca Plate is subsiding underneath the North American plate. Currently, scientists are predicting that there is about a 37% chance that a megathrust earthquake of 7, 1 or greater magnitude in this fault zone will occur in the next 50 years. The last known full margin rupture, on January 26, 1700, produced an estimated magnitude 9. 0 earthquake that caused the coastline to drop several feet, generated a tsunami that crossed the entire Pacific Ocean and struck Japan, and is recorded in both Native American oral histories and Japanese historical documents. That was 326 years ago. The fault has been locked and accumulating strain every single day since. Now let's talk about what the 2026 research has actually changed, because this is the part of the story that is not getting nearly enough attention. Scientists thought they understood the Cascadia Subduction Zone. They had mapped it, modeled it, and built an entire regional hazard framework around those models. New research published in April 2026 has revised 3 fundamental components of that framework, and each revision points in the same direction. The risk is larger than the previous model suggested. The first and most immediately significant revision concerns the depth of the subducting plate beneath northern Oregon. A new look at the Juan de Fuca tectonic plate beneath the coast of northern Oregon suggests this subducting slab is shallower than previously thought, with impacts on potential peak ground shaking during a Cascadia megathrust earthquake. We estimate that the slab interface is about 20 kilometers deep near the coastline, which is about 5 kilometers shallower than previous estimates. This could increase estimated peak ground acceleration, in other words, shaking intensity, from Cascadia megathrust earthquakes by approximately 9 to 17% along the coast of northern Oregon. 9 to 17% stronger ground shaking than previously estimated. In a seismic system where everything is already calibrated for one of the most extreme possible earthquake scenarios, discovering that the actual physics produces more intense shaking than the existing models calculated is not a refinement. It is a recalibration of the entire hazard framework that emergency managers, building code authorities, and infrastructure planners in the Pacific Northwest have been using. And it gets more complicated than just the depth. In a sedimentary basin, like the one discovered beneath Tillamook, sediments can act like a bowl of jello. Seismic waves strongly shake the weak material and get trapped against the basin edges, potentially allowing shaking to last longer as a result. These amplified seismic waves can be especially damaging to tall buildings and large structures, a hidden sedimentary basin beneath Tillamook on the northern Oregon coast. Previously unknown to seismologists building the hazard models for this region. Now confirmed to exist directly above the zone where new research says the fault is 5 kilometers shallower than thought. The combination of a shallower fault and a newly discovered basin that traps and amplifies seismic waves is precisely the kind of compound geological condition that turns already serious earthquake hazard estimates into something considerably more severe. The second major 2026 revision concerns the structural behavior of the fault itself. The Cascadia Subduction Zone isn't shutting down, but it's more complicated than previously thought. That headline from April 2026 research addresses a specific idea that had been circulating in some interpretations of seismic data that the northern section of the Cascadia Subduction Zone might be entering a period of reduced activity, potentially reducing earthquake risk for communities near Vancouver Island and the northern Washington coast. The 2026 research is direct in its response to that interpretation. The zone is not shutting down, it is more complex. A recent survey of the seafloor found that the fault can be separated into at least 4 geologically distinct segments. Each one may be insulated from a rupture in another region. In this study, the researchers took a closer look at 2 of the regions by analyzing data from 3 monitoring stations, 1 near Vancouver Island and 2 off the coast of Oregon. 4 geologically distinct segments, each potentially insulated from rupture in another region. This segmentation matters enormously for how hazard is assessed and communicated. It means that a future Cascadia rupture may not necessarily run the full 700-mile length of the fault simultaneously. It may initiate in one segment and propagate, or not propagate, into adjacent segments, depending on the specific stress conditions at each boundary. And it means that a moderate earthquake, like the June 29th magnitude 5 event at the southern doorstep of the zone, may represent stress redistribution within one segment, rather than a precursor to a full margin rupture. Or it may represent something else entirely. The honest scientific answer is that distinguishing between those scenarios in real time remains one of the most difficult problems in operational seismology. The Cascadia Subduction Zone is a 700-mile fault stretching from northern California to British Columbia and separates the Juan de Fuca and North American tectonic plates. Tectonic plates, which are massive slabs of solid rock that float on the Earth's mantle, can cause earthquakes and volcano formations at the surface as they shift and subduct. The process during which the plates collide and one is forced beneath the other, typically denser plate. And the specific phrase in the ABC News reporting from May 2026 that describes what is happening to the northern portion of this boundary, the Earth beneath the Pacific Northwest is tearing apart, is not hyperbole. It is a description of a genuine structural phenomenon that researchers are documenting with new precision using the expanded monitoring network now operating in this region. The tear refers to what happens at the northern edge of the Juan de Fuca Plate as it subducts. The plate is not entering the subduction zone as a single uniform slab. It is fracturing and segmenting as the older, colder northern portions behave differently under the same tectonic stresses than the younger, warmer southern portions. This differential behavior at the northern boundary is part of what makes the region geologically complex and part of what makes the standard modeling of Cascadia hazard inadequate for the northern section specifically. Now let's address the question that the title of this script poses directly. Is the June 29th magnitude 5.5, or any of the moderate seismicity that has been occurring along this boundary in 2026, a foreshock to a larger event? The honest scientific answer, stated as clearly as possible, is we do not know, and current seismological tools cannot tell us. This is not a hedge or an evasion. It is the accurate description of where earthquake science stands in 2026. After every large earthquake in history, seismologists have been able to identify foreshocks in the data, events that preceded the main shock by hours, days, or weeks. But they can only be identified as foreshocks after the main shock occurs. Before the main shock, those same events look identical to ordinary seismicity that is not followed by anything larger. The mathematical problem of distinguishing a foreshock from background seismicity in real time has not been solved. It is one of the hardest open problems in the field. What can be said with confidence, based on the research published in 2026, is this. The Cascadia Subduction Zone is in a state of stress accumulation that has been building since 1700. The fault is 5 kilometers shallower beneath northern Oregon than models had previously estimated, which increases projected shaking intensity by 9 to 17%. A previously unknown sedimentary basin has been identified beneath Tillamook that will amplify and extend the duration of shaking during any future rupture. The fault has 4 geologically distinct segments, and the northern boundary region is experiencing active structural changes that are being monitored with increasing urgency. And moderate seismicity has been occurring at the southern doorstep of the zone in the weeks and months leading up to July 2026. None of those facts constitute a prediction, but they collectively constitute the most detailed and most sobering picture of Cascadia hazard that has ever existed, and they provide the context within which every earthquake at this boundary deserves to be understood. The Cascadia Subduction Zone will create a massive earthquake that will cause catastrophic damage. The Cascadia Subduction Zone is capable of generating a devastating earthquake at any time. On average, the zone produces a 9.0 or larger magnitude earthquake about every 400 to 600 years, although intervals have been as low as 200 years and as high as 1,000 years. We are 326 years past the last full margin rupture. The statistical return interval includes scenarios where 326 years is well within the middle of a normal inter-event period, and it includes scenarios where we are already overdue. The direct shaking hazard from a Cascadia rupture is geographically focused. The most intense effects would be concentrated within roughly 100 kilometers of the coast, covering portions of Northern California, Oregon, Washington, and coastal British Columbia. But the consequences of a full margin Cascadia rupture are not contained within that zone. A magnitude 9.0 or greater earthquake along the full length of the subduction zone would generate a significant Pacific-wide tsunami. A Pacific-wide tsunami, not a regional wave event. A tsunami that crosses the entire Pacific Ocean and reaches every coastline from Japan to Chile, from Hawaii to Alaska. The 1700 rupture produced exactly that. Japanese historical records document the tsunami that arrived on their shores within hours of the earthquake that no one in Japan felt. The same physics that produced that event in 1700 are operating today. The only thing that has changed is our awareness of them, our ability to measure them, and the size of the population living in the coastal inundation zones. Oregon has the potential for a 9.0 plus magnitude earthquake caused by the Cascadia Subduction Zone and a resulting tsunami of up to 100 feet in height that will impact the coastal area. There's an estimated 5 to 7 minutes of shaking or rolling that will be felt along the coastline, with the strength and intensity decreasing the further inland you are. 5 to 7 minutes of continuous shaking, not the 30 to 60 seconds that characterizes most damaging earthquakes. 5 to 7 minutes, buildings not designed to survive that duration will fail. Infrastructure not engineered for that shaking will fail, and anyone in a coastal inundation zone who does not reach high ground in the minutes after the shaking ends will face a tsunami. In Cascadia, episodes of slow fault slip and their associated seismic signal are often referred to as episodic tremor and slip, or ETS. These events occur regularly in Cascadia, roughly every 8 to 22 months, and are imperceptible to humans. The ETS events are the fault quietly slipping in deep segments below the locked shallow zone. They do not release the stress that is accumulated in the locked zone. They are the fault's lower segments relieving their own pressure, while the upper locked section, the section that will produce the catastrophic rupture when it finally gives, continues to accumulate strain uninterrupted. Finding this link between fluids coming to the shallow subduction zone is pretty unique, as is the evidence that the fault is not completely locked. The presence of fluids at the shallow subduction interface is a finding that adds another layer of complexity to the existing hazard framework. Fluids along a fault plane can influence how and when that fault ruptures. They can reduce the friction that keeps the fault locked. They can change the propagation dynamics of a rupture once it initiates. Their presence at the shallow Cascadia interface is a discovery with implications for hazard models that are still being worked out in the research literature. The practical message for everyone living in the Pacific Northwest is unchanged by the 2026 research, but made more urgent by it. Know your tsunami inundation zone. Know the evacuation routes from it. Know that in a Cascadia event, official warnings may not arrive before the tsunami does. The earthquake shaking itself is the warning, and anyone who experienced prolonged violent shaking near the coast should move to high ground immediately without waiting for any other signal. Have emergency supplies ready. Have a communication plan with family members. Understand that the infrastructure you depend on daily, roads, bridges, utilities, communications, will be severely disrupted by a full margin Cascadia rupture, and plan for the possibility of being self-sufficient for days to weeks. The question of whether the June 29, 2026 magnitude 5.5 and the broader seismic activity along the northern Cascadia boundary this summer represents a foreshock sequence to a larger event is one that cannot be answered today. What can be answered today is whether the people living in the Pacific Northwest are as prepared as the current scientific understanding of Cascadia's hazard demands that they should be. That answer, for most communities and most individuals, is no. Not because the science has been hidden, because the timeline of Cascadia's rupture cycle is longer than any individual human lifetime, which makes sustained preparedness genuinely difficult to maintain. But the research published in April 2026, the shallower slab, the hidden basin, the four-segment structure, the active tearing at the northern boundary, has made the case for urgency clearer than it has ever been. The fault is not shutting down. It is more complex, more dangerous, and more poorly understood at critical locations than previous models acknowledged. And somewhere in the 326 years of accumulated strain that has been building since 1700, the answer to when sits waiting in the geology, telling its own time indifferent to ours.